Okay, our next presenter will be Joseph Samaniego on investigation of coatings for Langmuir probes in an oxygen-rich space environment.
Thank you. Thanks. My name is Joseph. I'm from the University of Colorado. Where's the little clip? Oh, here it is. I'm going to be switching gears for a little bit from the arid climate of the moon and looking at the upper atmospheres of planets, specifically the space plasma environment and how those interfere with space plasma measurements through the use of Langmuir probes. So first, for those of you guys who are unaware or have forgotten, quick review about Langmuir probes. They're very simple instruments, maybe. Whoa, okay, that's weird. They're very simple. They are nothing more than a conductor inserted into a plasma. You then sweep a voltage. Across the plasma, and then that will you measure the current both emitted and collected by that. From these curves, the semi-log and the first derivatives, you are able to determine plasma potential, density, and temperature of that plasma. These are relatively well-used instruments. They've been used the better part of the half-century and have a good track history. However, it's been shown recently that these probes have issue when exposed to oxygen-rich space environment. Specifically in MAVEN, we can see here degradation of the probe after long exposure times to oxygen. This should have looked like this curve to the far right, but instead you can see is much more noisy. So in the upper atmosphere of planets, the ionosphere specifically, there's a lot of we all know that molecular oxygen is highly reactive, but atomic oxygen even more so, and is thought to be created by photodissociation of the diatomic oxygen into molecular diatomic oxygen into atomic oxygen. The question then is what happened to is whether or not the MAVEN probes did indeed experience oxidation, and what the effect is of what the general effect is of oxidation on the surface of Langmuir probe. Additionally, MAVEN was using a titanium nitride coating, commonly thought to, at least at room temperature, to be relatively inert. There are other common coatings such as DAG and gold. DAG has been shown in previous experiments to erode over time while in the presence of oxygen. And gold, while being inert at room temperature, has also been shown to degrade when bombarded by high energy oxygen atoms. So the objectives of the experiment was to characterize the effect of oxidation on Langmuir probes. If you made a measurement with a deteriorated probe, what could you expect from the measurements gotten? Then to see whether or not there were possible metals or materials that wouldn't oxidize in these plasma environments, and then to characterize them correspondingly. So we tested titanium nitride, gold, and DAG. These are commonly used coatings against test materials like copper and nickel, metals that are well-known, easily oxidized. And then we tested these against new coating materials, Rhenium and Iridium, in the hopes that those would not show any degradation. The reason we chose Rhenium and Iridium was that Rhenium and Iridium both have their oxidized layers are highly conductive, and our thought was that the oxidized layers in the previous cases might add a resistor in the circuit that would impede that as you take the voltage sweep, that would shift the curves. So then, in order to test this, we set up we had a two-chamber method. First, each one of these probes, there was a wire probe, as I showed at one of the very first slides, of each metal. Titanium nitride, gold, all of them. Each one of these probes were put into put into an argon chamber, or a vacuum chamber with argon gas. Plasma was created. The probes were cleaned via in situ methods, and then a data sweep was taken for a control measurement. Once control measurements, the probes were removed from that chamber, and moved into the oxygen chamber, where an oxygen plasma was introduced with the addition of UV lamp to photodissociate diatomic oxygen into atomic oxygen. The probes were exposed there for about 20 minutes and then removed and replaced back into the previous argon chamber where they were again swept to see how the curves change after exposure to oxygen. The results of this are shown here. And paralleling the first 3 graphs that I showed at the very beginning of the slide, we see here the black and blue are, oh, I'm sorry, one other thing. While the probes were in the argon chamber, after the control sweep was taken, they were cleaned by the same in situ methods as they were at the beginning to see whether or not this oxidized layer could be removed. This was done for 2 reasons. One, to see whether or not this layer could be removed by a spacecraft. Additionally, it was to make sure that we had indeed recreated the exact same plasma environment and that we weren't measuring, and the change due to oxidation wasn't due to a change in, my air against Lee. You see here that the black and blue, that's the before, and the recleaned, those overlay very nicely in all these cases. The red is after oxidation. You can see here the copper. This shows the most exaggerated effect the most exaggerated effect due to oxidation, and is what we talk about when we characterize the effect of oxidation on a Langmuir probe. We see that the IV curve shift to the right. The knee here measures the plasma potential also shifts, and there's a stretching of the retarding region where you would measure the temperature. So in general, the knee shifts more positive, the knee rounds, and the retarding region stretches. This is somewhat corresponding to what we would expect for a resistor in the circuit. If there is a resistive layer, we'd expect something of this order. Then we tested the current coating materials to see how those would react when introduced to plasma, or oxygen plasma. The titanium nitride not only had significant effect due to the oxygen plasma, but also would not return to the control sweep, no matter how hard of a current I tried to clean this with, which stands to suggest that once the titanium nitride gets oxidized and becomes titanium oxide, that is either in a lower energy state and it's stuck. It's stuck that way. It's not a layer that you're going to be able to off gas or burn off. This is an actual chemical change in the composition of the layer. Gold did have an effect after oxidation, more so than you would expect for the common knowledge, conventional thinking that gold is inert. And then DAG showed very little change before and after oxidation, but again has the issue of eroding when it's in the oxygen, when it's in an oxygen plasma. Then of the new coating materials, Rhenium showed pretty much the same response as the DAG, but the Rhenium has the benefit of it doesn't have a lifetime; it doesn't erode over time. And Iridium, frankly, did great. The curves stacked up one on top of each other, almost perfectly. So, which definitely seems to suggest that for a new probe coating, for a Langmuir probe that is intended to be used in the upper atmospheres of planets, magnetospheres, etc., anywhere where there's going to be a lot of atomic oxygen, Iridium definitely shows promise as being a candidate for these probes. Then to characterize how the curves actually come out in measured plasma parameters, because at the end of the day, you don't care so much about the curve, you care, what is the instrument telling you. So these 3 graphs show here the the plasma potential, temperature, and density, and you can see for the most part, the plasma potential, just as the curves, the knee shifts to the right, and the plasma potential follows. The temperature gets a little bit hotter. Most of it seems unchanged. However, for copper and the rest, you can kind of see that there is a shift to the right, meaning that if you'd measure the temperature via an oxidized Langmuir probe, you would measure a hotter temperature than is expected. And pretty much across the board, the measured electron density of the plasma decreases. So as a general rule, you would, if you were using a oxidized Langmuir probe, you'd expect a more positive plasma potential than what is real, a hotter electron temperature than what is real, and a lower electron density than what is real. Then how does, comparing then our results to MAVEN, they seem to corroborate almost everything except for the fact that MAVEN seems to be a whole lot worse. This is due to a couple reasons. One, the Langmuir probes on MAVEN weren't turned on immediately. They went through many dips, several months, I think, into the Martian atmosphere, several dips into the Martian atmosphere, testing other instruments before the Langmuir probes were ever turned on. So it's highly likely that that any oxidation that would have happened had already happened. To put that into context, to put that into context, our 20 minutes in our chamber corresponded to 1.5 dips into the Martian atmosphere. So if MAVEN was flying for months, into the Martian atmosphere, making a dip roughly every 4 hours, then the titanium nitride probe was about as degraded as possible. So in conclusion, titanium nitride was, frankly, pretty bad for a coating that used for coating on a mission that was intended to go to an oxygen-rich space environment. Gold was worse than expected. DAG was surprisingly good, but does erode over time. Rhenium had similar results due to DAG, but didn't have the negative effect of eroding over time and having a lifetime. These results, Iridium did great. These results can be paralleled to other plasma instruments such as RGAs and electrostatic analyzers. If we wanted to parallel these results, however, to electric field probes, we need to do some additional work to look at how the work function changes of Iridium and Rhenium after exposure, to look at photo emission. Once that gets characterized, we'll be able to make a statement as far as how Iridium might work as an electric field probe. And with that, I'd like to say thank you. Any questions? All right. All right, thank you.
And next presenter will be Mark Cohen. Mark will talk about sample receiving lab and planetary quarantine facility for the deep space gateway.
Hello.